All right, welcome to The Explainer. Today, we're going to be data detectives. We're taking what looks like a totally normal spreadsheet full of car specs, and we're going to dig deep to uncover the stories hiding between all those rows and columns.
So, you might be thinking, a spreadsheet, really? But trust me, we're about to go on a guided investigation here. We're going to ask a few key questions and see what secrets this data is holding about the engineering, the economics, and even the design of the cars we see every day.
So here's our plan. We're going to tackle 4 big questions. First, we'll dive into engine power. Then, we'll zoom out and look at fuel efficiency across the globe. After that, we'll try to crack the code of a car's price tag. And finally, we'll hunt for a hidden link in car design. Each step is going to reveal something new.
Okay, first up, let's start with a classic debate you hear all the time among car people. Does bolting on a turbocharger actually give a car a real, measurable boost in power, or is it all just hype? Well, the data has an answer.
Right off the bat, the answer seems pretty obvious. The standard engines in our dataset, the ones without a turbo, they average about 99 horsepower. The turbo engines, they're way up at 123.4. That's a jump of over 24 horsepower. But here's the thing with data. You always have to ask, is this a real, meaningful difference? Or did we just get a lucky sample of cars?
To find out for sure, we got to pull out the right tool. And for this job, we're going to use something called a t-test. Honestly, the best way to think about it is like a statistical magnifying glass. It lets us zoom right in on the difference between our two groups, turbo and standard, and see if that gap is a real deal.
So the t-test spits out this one super powerful number called a p-value. And for us, that number is tiny, 0.00012. Now in statistics, the general rule of thumb is that any p-value less than 0.05 is a big deal. It means your result is statistically significant. Our number isn't just less than 0.05, it's way, way smaller, meaning the chance of this being a random fluke is almost zero.
So our investigation confirms it. The numbers totally back up what drivers feel on the road. That extra surge of power you get from a turbo engine, it's not just in your head. It is a very real, statistically significant advantage. First case closed. All right, let's move on to our next question. We've looked under the hood, so now let's zoom out and take a look at the whole globe. We're going to investigate if there's sort of a fuel economy battle happening between continents. When it comes to how much gas a car uses, does it matter where it was made?
So, our data set has cars from 3 major hubs, Asia, Europe, and North America. But this brings up a new problem. Our t-test, that awesome magnifying glass we just used, it only works when you're comparing 2 groups. Now that we have 3, we have to grab a different tool from our kid.
So, we're bringing in something called ANOVA, which stands for Analysis of Variance. The easiest way to think of ANOVA is like statistical referee. Its job is to look at all 3 of our teams on the field, Asia, Europe, and North America, and decide if there's a real significant difference in the average performance of at least one of them.
And what's the ref's call? Just like before, ANOVA gives us a p-value. And again, it is incredibly small. It tells us that the probability of seeing these differences in fuel consumption, just by random chance, is less than 0.01%. That makes it extremely unlikely to be a fluke.
This leads us to our second big discovery. It's not a coincidence. Where a car is engineered and built is a major factor in how much fuel it uses, especially for city driving. Different design philosophies and regulations around the world leave a clear fingerprint right in the data.
Okay, now for our most ambitious question of the day. We're switching from comparing to predicting. Can we use our data to kind of reverse engineer our car's price tag? Can we find that secret formula that explains why one car costs 10 grand and another costs 40? To do this, we've rounded up 5 key suspects, features that we think have a big influence on price. We're looking at engine size, horsepower, the car's width and length, and its city fuel consumption. Let's see which of these are the real culprits behind a high sticker price.
Our tool for this is called multiple linear regression. It sounds complicated, but you can think of it like a prediction machine that creates a recipe. The final dish is the car's price, and our suspects are the ingredients. Regression's job is to figure out the exact amount of each ingredient, like how much a little more engine size adds to the price, or how a bit more width affects the cost.
Okay, so check out the final recipe. This is fascinating. Look at the stars. A bigger engine and a wider car are highly significant. They really drive the price up. And surprisingly, so is worse fuel economy, which probably means the thirstier cars are also the more powerful or luxurious ones. But notice what isn't a major factor here: horsepower and length. This suggests that once you already know how big the engine is, knowing the exact horsepower doesn't really add much more to the price prediction. So just how good is our price recipe? That's where this number comes in. It's called the R-squared value, and it tells us the percentage of a car's price that can be explained by our model. And our score is a whopping 82%.
I mean, think about that. That's incredible. Yeah, there's brand, materials, and other stuff, but we now know that a massive 82% of the price difference between cars in this data set comes down to just these 5 technical specs. We've cracked a huge piece of the code.
All right, for our final question, we're looking for a hidden connection, kind of like a secret handshake in car design. We want to know if there's a link between 2 basic choices. The body style, we'll look at sedans versus hatchbacks, and the drive wheels, so front wheel versus rear wheel drive.
This table is the heart of this investigation. The first number in each box is what we actually saw in our data. For example, we found 49 front-wheel drive hatchbacks. The number in the parentheses is what we'd expect to see if there was absolutely no connection at all. The closer these two numbers are, the less likely there's a real link.
And this chart just helps us see that same data visually. You can see the distribution pretty clearly. For sedans, front-wheel drive is way more common. For hatchbacks, it's a bit closer. But the big question is always, is this difference big enough to matter, or is it just a quirk in our data set?
To get a final answer, we use our last tool, the chi-squared test. Its entire job is just to measure that gap between what we observed and what we expected, and then tell us if that gap is too big to be random.
And the result, the gap was just too small. Our p-value was well above that 0.05 cutoff point, so we found no statistical evidence of a secret handshake. In this data set, the choice to make a car a sedan or a hatchback doesn't seem to be connected to the choice of which wheels get the power.
So what's the big picture here? We started with a plain spreadsheet, but just by asking the right questions and using the right tools, we found out that turbo power is real, that a car's origin really matters for fuel use, and that we can explain 82% of its price with just 5 variables. The real takeaway isn't just about cars. It's that data isn't just numbers. It's a collection of stories just waiting for a curious detective to come along and read them.